All right, guys, time to conduct some test. The z-test and the t-test. I'm going to do it together because there's not too much of a difference between those two. And we're going to start off with the traditional method. But when it comes to the type of test, it depends on if we know the population standard deviation or not. The z-test is a statistical test for the mean of a population. It can be used either when the sample size is greater than or equal to 30 or when the population is normally distributed and the population standard deviation is known. The t-test is similar in definition, except the population standard deviation is unknown. Going back to the diagram that I drew for confidence intervals when it comes to a test. If the population standard deviation is known, we're going to be using a z-test. And here's the z-test formula. And we use it when sigma is known or when the standard deviation is mentioned before the sample is introduced. It is a t-test when the population standard deviation is unknown. I should put unknown right here. And when we do not know the population standard deviation, we will have to use S. And S is the sample standard deviation. Or you will be using the t-test when the standard deviation is mentioned in the same sentence as the sample. For the traditional method, here are the steps that you're going to utilize. Step number 1, you want to write your null and your alternative hypotheses. We went over how to write that already. Step number 2, you want to find the critical values. But when you want to find the critical values, you must determine what kind of test you're going to run. And I'm just going to get rid of this for a second. And I'm going to put here z-score file. Now, ask yourself the question, is sigma known? If the population standard deviation is known, so if we know the population standard deviation, that is a z-test. And you must give the direction of the test, the alpha level, and then you're going to go into the z-score file using the direction and the alpha level to find the critical value. If it's left-tailed, the critical value is negative. If it's two-tailed, it is plus or minus, positive or negative. If we do not know the population standard deviation, that is a t-test. Direction must be given, alpha must be given, find your degrees of freedom, and use the t-distribution to find the critical value. If it's left-tailed, the critical value is negative. If it's two-tailed, the critical value is both positive and negative. Step 3. Compute the test value. If it is a z-test, you're using the top formula to compute the test value. If it is a t-test, you're using the bottom formula to compute the test value. Step number 4, make the decision. Draw the bell-shaped curve and place the critical values on the curve and shade the curve. If the test value falls within the shaded area, reject the null hypothesis. If the test value falls within the non-shaded area, we do not reject the null hypothesis. And then number 5 is to summarize the results. If the null is rejected, we can state that there is enough evidence, usually to support the claim. Support the claim. And if we do not reject the null hypothesis, there is not enough evidence to support the claim. So look here. If the null is not rejected, there is not enough evidence. Not goes with not. If it is rejected, there is enough evidence to support the claim. So the is goes with the is. Is not goes with is not. And that is how you can determine if there is enough evidence to support the claim or if there's not enough evidence to support your claim or the claim that we are investigating. So in this video, we're going to run two tests. We're going to do two questions. One will be a z-test, one will be a t-test, and then you must determine which one is which. The Medical Rehabilitation Education Foundation reports that the average cost of rehabilitation for stroke victims is $24,672 with standard deviation of $3,251. To see if the average cost of rehabilitation is different at a particular hospital, a researcher selects a random sample of 35 stroke victims at the hospital and finds that the average cost of their rehabilitation is $26,343. At the alpha level of 0.01, which means we are allowing a maximum of 1% of type 1 error, can it be concluded that the average cost of a stroke victim, can it be concluded that average cost of stroke rehabilitation at a particular hospital is different from $24,672? Step number 1 says state the hypothesis and identify the claim. Now remember, the null hypothesis states that there is no difference between a parameter, which is the population mean, and a value that represents the population mean, which is that specified value. Now the value that we're looking at is $24,672. Remember, the parameter is mu, and mu is the population mean. So for our null hypothesis, we're going to state that mu is equal to $24,672. Now somebody may ask why we're not using the $26,343, because this comes from the sample and we're trying to test the population mean. We're using the sample information to test it against the population mean. And I'm going to show you in a minute why we're using 24,672. The null hypothesis, the alternative hypothesis states that there is some sort of difference between the parameter, which is mu, which is the population mean, and a specific value that represents the population. Now, if you look at the last sentence, it says, can it be concluded that the average cost of stroke rehabilitation at a particular hospital is different from $24,672? Different does not specify any direction. It can be more, it can be less. So this indicates that it is two-tailed. So for my alternative hypothesis, we are stating that mu does not equal to $24,672, and that is the claim. That is what we're trying to conclude. We're trying to see if there is some sort of difference than the cost of $24,672. Once again, these two values must be the same, and the null hypothesis states there's no difference. That's why it is equal. Step number 2 is you want to find the critical value. You got to know what kind of test you're running, if it is a z-test or if it is a t-test. We know it's two-tailed already, so I'm going to put the two-tailed right here. And though the alpha level is 0.05. On your exam, you won't have it broken down like this. So you must refer back to this information right here. If the standard deviation is mentioned before the sample is introduced, this is a z-test, and that means sigma is known. If the standard deviation is mentioned in the same sentence as the sample, that is a t-test, which indicates sigma is unknown. So the question is sigma known? And the answer to this question is yes. And the reason why it is yes is because the standard deviation is mentioned before the sample is introduced. Because the standard deviation is mentioned before the sample is introduced, this is a z-test. So we know it's a z-test. It's a two-tailed test with 0.05 as the alpha level. Actually, I lied. It is 0.01. Excuse me. It says it right there, 0.01. So we're going to go to the z-score file. This is a two-tailed test, 0.01. So therefore, the critical value is positive and negative 2.58. Okay. Step number 3 is compute the test value. And we're going to use the z-test formula to compute the test value. Now, I'm going to fill in information that we should already know. Mu, which is the population mean, which is stated right up here, that is 24,672. So you should know that off the back because you're using that for your hypothesis. N, our sample size. We have a sample of 35 stroke victims, so N is 35. The population standard deviation is 3,251. And remember, X bar is the sample mean. From the sample of 35 stroke victims, the average was $26,343. That is the sample average. You guys have to know your symbols as well and what they mean. Let's compute our test value. Z equals to the sample mean, which is 26,343, minus the population mean, which is 24,672, divided by the standard deviation of our population, which is 3,251, divided by the square root of the sample size to the square root of 35. Our final answer should be 2 numbers after the decimal because we're dealing with z-scores. Let's do the top. That equals to 1,671. Let's do the bottom. 3251 divided by the square root of 35. Let's take 2 numbers after the decimal. 549.52. Let's divide that. 549.52. Oops, let's delete that. 52. And the z-score should be 2 numbers after the decimal. So z is equal to 3.04. Okay. Now that we computed our test value, we're going to make our decision whether to reject or do not reject the null hypothesis. So we're going to follow the directions when it comes to making our decision. We're going to draw the bell-shaped curve. And then we're going to place our critical values on the bell-shaped curve. It's two-tailed, so 2 critical values. Our critical values is negative 2.58 and positive 2.58. Okay, let's shade into the tail region. Shade into the left. And then we're going to shade into the right. Now remember, if our test value falls within the critical region, we reject the null hypothesis. If it does not land within the critical region, we do not reject the null hypothesis. Our test value is 3.04. And 3.04 will fall somewhere over here. 3.04. And because it falls within the shaded area, we are going to reject the null hypothesis. Reject the null hypothesis. So I'm going to zoom out for a second. The null hypothesis, which is right here, we are rejecting it. So we're going to cross that out. Okay, that didn't go too well. We crossed out the null hypothesis, which means we're going to have to look at the other one. And the other one is our claim, which means there is enough evidence to support our claim. Let me erase that. Let me put it back. I'll erase it when I'm done, when I post this as a PDF. So remember, if we reject the null hypothesis, there is enough evidence to support the claim. There is enough evidence to support the claim that the average cost of stroke rehabilitation is different from $24,672. And that is it. That is our 5 steps of hypothesis testing. Okay, let's run one more kind of test. Number 5 says, a researcher believes that the mean age of medical doctors in a large hospital system is different than the average age of doctors in the United States, which is 46. A random sample of 30 doctors from the system is selected, and the mean age of the sample is 48.6, and the standard deviation is 7.2. Is there enough evidence to support the researcher's claim at the alpha level of 0.05? Assume the variable is normally distributed. Okay. Let's write our null and alternative hypothesis. Once again, the null states that there is no difference between a parameter and a specified value that represents your parameter. The parameter is mu. The alternative specifies that there is some sort of difference. And the alternative is the claim. What is the researcher claiming? Or what does the researcher believe? Well, they believe that the mean age of medical doctors in a large hospital system is different than the average age of doctors in the US, which is 46. The word is different. So different indicates that it can be older or it can be younger. It can be greater. It can be less than, or it can be lower. So I'm going to write my alternative hypothesis first. Mu, what kind of mu is that? Mu does not equal to 46 years of age because it says that it is different. And that is the claim. Now, when it comes to the null hypothesis, there is no difference between the parameter, which is mu, and a specified value that represents the parameter, and that is going to be 46. We know that this is a two-tailed test because of the word stating that it is different. And the alpha level is 0.05. But once again, you must do this in order when it comes to your examination, because you won't have these indicators here. You have to know them. Is sigma known? And the answer is no. Sigma is unknown. And therefore, we're using a t-test. How do we know that we do not know the population standard deviation? Go back to the work. If the standard deviation is mentioned in the same sentence as the sample, that is a t-test. That means we do not know the population standard deviation. And if you look here, a random sample of 30 doctors had a mean age of the sample of 48.6 and a sample standard deviation of 7.2. The standard deviation is mentioned in the same sentence as the sample. Therefore, it is a t-test, and we must find our degrees of freedom before we find our critical values. So degrees of freedom is the sample size minus 1. We're looking at 30 doctors, so our degrees of freedom will be 29. The critical values for a two-tailed test is going to be both positive and negative. Let's clear that. This is a two-tailed alpha, 0.05. Degrees of freedom is 29. And so the critical value that we have here is 2.045. Once again, because it is a two-tailed, we're going to have negative 2.045, positive 2.045. Step number 3 is compute our test value. Let's do that. We know we have 30 doctors in total. Mu, which is the parameter, the population mean, that is 46. Once again, that is stated right up there. The sample standard deviation for this question is 7.2. And the sample mean age for those 30 doctors were 48.6. So T is equal to 48.6 minus mu, which is 46, divided by S, which is 7.2, divided by the square root of N, square root of 30. Okay. T is equal to, let's do 3 numbers after the decimal when it comes to a t-test. That is going to be 2.6 divided by, that's going to be 7.2. Let's clear that. 7.2 divided by the square root of 30. Take 3 numbers after the decimal. That's 1.315. Let's divide 2.6 with 1.315 and take 3 numbers after the decimal. And that's approximately 1.977. That is our test value. All right. Step number 4 is going to be make a decision. Either we're going to reject or not reject the null hypothesis. This is two-tailed. Let's place both critical values on, which is negative 2.045 on the left, positive 2.045 on the right. And we can shade into the tail regions. Now remember, if the test value lands in the shaded area, we're going to reject the null hypothesis. So let's put that over here. Reject the null hypothesis. Reject the null hypothesis. If the test value lands in the non-shaded area, do not reject the null hypothesis. Okay. Our test value is 1.977. That will fall on the right side of the distribution, but it will not fall past 2.045. It will fall right there, 1.977. Because it does not fall within the shaded area, which is the critical region, do not reject the null hypothesis. That is your decision. So that means we're going to go back up to our hypotheses. For our null, we do not reject it. If we're not rejecting our null, then we are accepting it. And because we accepted the claim that is not ours, because we did not reject that, when we write our summarization, we are stating that there is not enough evidence to support the claim. So, to summarize the results, there is not enough evidence to support the claim that the average age of medical doctors in a large hospital is different than 46. All right, guys. I'll catch you in the next one involving hypothesis testing using the traditional method. Take care.